In this lesson, I'll show you how to calculate work when force is applied linearly or parabolically. Now, before we begin, let's take a look at how we calculated work when the force was applied constantly. We used the formula force times displacement, where W is equal to F times S. Now, if you take a look at this graph, where force is on the y-axis and displacement's on the x-axis, the amount of work equals to the area of this region here. And you find the area of a rectangle by taking the length times the width, and that's exactly what we do. But when the force being applied is linear, as you would find when compressing a spring, where the force grows by a specific factor the further it's compressed, you get a graph that looks like this. Notice the area underneath the line is a triangle, and unlike a constant force, where the area underneath is a rectangle, here it's a triangle, so we use base times height divided by 2. In this illustration, the base and the height are represented as x. So x times x is x squared, then we divide by 2. Now, depending on the level that you're studying this, another way to come up with the formula for work when force is applied linearly is by taking the integral of this line. Either you can remember how to take the integral of a line, or just memorize this formula. Also, don't forget that every spring is unique. So we multiply this formula by a constant k depending on that specific spring. We'll discuss how to come up with the formula for work when force is being applied parabolically in question number 3. So with that being said, let's begin with question 1. Calculate the work performed in compressing a spring with a force constant of 200 newtons per meter the first 3 centimeters. So since we're working with newtons in meters, this number right here needs to be in meters. So let's change that into meters first. It's 3.0 times 10 to the power of negative 2 meters. Remember, work has the units newtons times meters, and that's the same thing as saying joules. Now, using the formula that we just derived, where work is equal to the constant k times x to the power of 2 over 2, we'll substitute k with 200. So I have 200 newtons per 1 meter. Multiply that by x, which represents the displacement, and in this case it's 3.0 times 10 to the power of negative 2, and the units here are meters. Raise that to the power of 2 over 2. You see this power of 2 here? That applies to both this number and the meters. And the reason why that's important is because if we square the meters, we have meters squared. If we have meters squared up here and meters at the bottom, this unit and this unit will cancel out, where you're only left with a single m. So now that that's done, we can go ahead and multiply 200 times 3.0 times 10 to the power of negative 2 is the same thing as saying 0.03, and that needs to be raised to the power of 2. Then we divide this number by 2, which gives us 0.09, and remember the units for work are newtons times meters, or joules. You can just write down joules instead. In question number 2, calculate the work performed in compressing the same spring the next 3 centimeters. Now be very careful with this question because they specify the next 3. So between 3 and 6 centimeters of displacement. This number represents the amount of work between 0 and 3. So to come up with the next 3, let's find out the work performed from 0 to 6, then subtract this from that number. So we have work is equal to the same thing as before, 200 newtons per 1 meter times, now remember the displacement here is 6, we're going from 0 to 6, so 6.0 times 10 to the power of negative 2 meters raised to the power of 2 over 2. And rather than showing you the cancellation process, let me just replace this with 6 and then divide by 2, and that is the amount of work from 0 to 6. 0.36 joules. Like I said, I'll subtract this amount from that, and that is equal to 0.27 joules. That's the amount of work that you need from 3 to 6 centimeters of displacement. All right, let's continue. For question number 3, what is the work performed in compressing a quadratic spring which has the formula F is equal to kx squared, with k being 2,000 newtons per meter squared from 0.30 meters to 0.40 meters. Now we haven't discussed the formula for work when it is parabolic force, and this chart shows you the different formulas that you can follow for when force is linear, constant, parabolic, etc. If you'd like to know how this formula is derived, again we use integrals. That's part of calculus. So this is what a parabola looks like when y is equal to x squared. For the area underneath the parabola, you increase the exponent by 1 and divide by that value. So in this case it would be k, our constant, x to the power of 3 over 3. Alright, from here our strategy is to find out the amount of work from 0.40 and find the amount of work from 0 to 0.30 and subtract those two numbers. So first we'll find out from 0 to 0.40 meters of displacement, and then again 0 to 0.3 meters, then subtract this value from the bigger value. And we'll replace this k value with 2,000 newtons per meter squared. Work is equal to 2,000 newtons per meter squared. Our x value is 0.40 meters raised to the power of 3 over 3. This exponent of 3 is distributed to the number and to the unit. We have meters cubed. 2 of these gets cancelled with both of those, leaving us with meters at the top and newtons. Okay, our calculator, 2,000 times 0.40 raised to the power of 3 divided by 3. Remember this value, 42.6 repeating joules. Let's modify what we placed into here. I'll change that with 0.30, divide by 3, and that gives us 18. I'll subtract 18 from 42.6. So 42.6 repeating minus the answer we just got, and that is 24.6, 24.6 joules repeating. And if we want this to the correct number of significant figures, we should write down 25 joules for simplicity. And there you have it. That is how to calculate work required to compress a spring when force is applied linearly and parabolically.